The last talk of this afternoon's session for the Earth Geo Atmosphere Ocean track is from Sean Freeman. We'll be talking about tobac. Sean is an assistant professor of atmospheric and earth science at the University of Alabama, Huntsville, having started that appointment in spring of 23. Before coming to UAH, he received undergraduate degrees in computer science and meteorology from Florida State University, an MS and PhD degrees in atmospheric science from Colorado State University. His research interests are primarily in clouds and storms. In particular, understand the kinds of environments that support cloud development and severe weather. He uses numerical weather modeling, advanced data science tools such as cloud tracking to uncover the basic building blocks of convection, from models to observations, as well as new measurements of convective inflows and outflows with drones. He served as a tobac lead developer since 2021 and has chaired the tobac steering committee since 2023. Outside of work, he enjoys photography, hiking, traveling, baking, curling, and watching college football.
All right. Thanks, Max. That was a great introduction, and then I realized that I had written that later. I appreciate the introduction, though. Before I get started, as Max said, I'm Sean Freeman, University of Alabama in Huntsville. I want to acknowledge this is a large team. I'll talk more about the team later on in kind of the second half of the talk, but I've put not everybody that's ever touched the code base on here, but this is close to it. People that have contributed ideas, people that have touched the code base, people that have found money for us. And my work here, this is just my work that's being sponsored by, or funded by the U.S. Department of Energy and NASA through the NASA ANCUS project. So tobac is a project, a package that's designed in atmospheric science. And so I want to give a little bit of background on why we're interested in this in the first place, because I'm guessing that at least some of you here aren't atmospheric scientists. I love clouds. I love talking about clouds. I was very excited yesterday on my flight in. We had flying from Atlanta, we had some nice bubbling storms up all the way for about an hour and a half on our flight, and I got to look at a lot of clouds and storms. Made me really happy. So how do we analyze clouds, right? I'm a scientist. We're interested in studying these in a statistical way, not just looking at them. Let's take a look at a single data set, and in fact, not even a single data set, a single snapshot of a single day at a single time from one data set. This includes 3 different variables in it, red, green, and blue. But this is our GOES 16 full disk. We have these geostationary satellites above us taking pictures of us all the time and in a variety of different bands. So one of the ways we can analyze clouds is by doing bulk statistics. Things like cloud fraction in a given area, how much of it's covered by cloud versus how much of it's not. Brightness temperature average, I'm not going to go into detail what that means. Think about it as cloud top height. Things like what is the average cloud top height, what is the maximum cloud top height. We can look at differences in regions. We can say what are the clouds looking like over the Seattle-Tacoma area versus what are the clouds looking like over the southeast right now. We can look at things like histograms. These are getting to kind of our bulk statistics, and these enable us to answer science questions like how does cloud fraction change over time, important for understanding climate? How do brightness temperatures change between regions, important for understanding localized weather and changes to land use, land cover change? We can also do things like individual case studies. If you watched the Twisters movie, that's what case studies are really all about in general, is going out, taking new observations, looking at a single system, a cloud, maybe a handful of clouds over a dedicated period of time. We use all of our instruments together. Usually you're adding in new instruments, and we're looking at it and we're saying, how does this one case evolve over time? What environmental conditions led to this specific weather system existing at this specific time with these properties? Well, one of the ways that we've kind of wanted to move into things is something that's a little bit of a hybrid between the two, which is object-based analysis of clouds. Things like cloud-by-cloud statistics, statistics on the processes of clouds, the lifetimes of each individual cloud. I'll talk more about that in a little bit. This enables us to answer new science questions like what is the average environment for storms that last longer than 60 minutes? How do brightness temperatures change before lightning initiation? Getting to fundamental questions that are really important for if you're out on the lake trying to understand, am I going to get struck by lightning or not? And things like how correlated are albedo, the amount of reflectance we get from the Earth, to things like brightness temperature, which we can measure from satellite. So as I mentioned, this has been of significant interest to the community for a long time, understanding how a single cloud changes over time. We call this a Lagrangian analysis, object-based analysis. We're taking a single cloud, we're studying it in its entire lifetime. We want to do this over and over and over again. The problem here is that atmospheric data sets are large. If I had an army of graduate students, I could probably task them to look at a full day's worth of data over maybe the continental United States, maybe even just a region, and they could identify all of the cloud life cycles and come up with insights about the cloud life cycles. But that is a single day at a single time. That's not how we actually want to understand the weather. There's millions of clouds present across the globe at any one time. This is from last month. This is the area around where I live, Huntsville, Alabama. This is about a 200 by 200 kilometer grid. This is GOES 19. I'm getting old. Visible satellite imagery here, and this just basically says what can we see from space in terms of satellite imagery. Every one of those little white specks, and they'll get smaller as you get further back in the room. Every one of those little individual white specks is a cloud. We want to understand what each and every one of those is doing over time. This is one afternoon in one relatively small region of the United States. This doesn't even cover a full state. There's not a full state represented here. There's parts of 3 different states. So just understanding that this is a really challenging problem if we want to get to those important scientific questions. And it's a data volume problem, really. And atmospheric data sets are diverse. This is satellite data. I've shown satellite data because satellite data is pretty. There is model and reanalysis data. We've already seen some of that if you've been sitting in here most of the day. Satellite data, radar data, and then things like individual observations. I have a weather station by the airport. I have a weather station in my backyard. Somebody has taken a hail observation, et cetera, et cetera. All of these come in different formats, different grids, different variables, and it makes dealing with all of it fairly challenging. And so this is kind of where the story of tobac begins. And I'm going to tell both how tobac works and also the story of how we got here and some lessons learned along the way. So in 2017, or around 2017, I was a baby graduate student, and a larger group, the GWEX ACPC working group, doesn't really matter what the group does, bigger group, important people, have decided that they wanted to look at the representation of how aerosols, small particles in the atmosphere, affect the formation of clouds in a variety of different numerical models of the atmosphere. So a key question of this is, how do we compare representations of clouds? We could do any of those methods we talked about before, but really the idea with how aerosol particles, small particles are affecting these clouds has to do with lifetimes. It's one of the key questions. So that really requires us to do cloud tracking. And really the thing and the question that birthed tobac was, how do we do this with over a dozen different numerical models and numerical model configurations? Every numerical model has its own grid, its own data format. It's the XKCD comic realized in real life in a very, very, very small scale. So that is the genesis of tobac, Tracking and Object-Based Analysis of Clouds Python package. It's a Python package designed to objectively identify, track, and analyze clouds and provide information on, I say clouds, I'm going to say clouds throughout this entire talk because I said I love talking about clouds. Tobac's been used for a variety of different things beyond clouds. If it's an atmospheric phenomenon, or really if it's a phenomenon that happens on a grid, we can track it. The idea behind tobac was it was one of the first packages of this genre to really embrace the idea of being grid and variable independent. So we can work on any gridded or semi-gridded data set. We have an X-ray backend. If you've heard of tobac before, that's new and very exciting to us because it took a long time to refactor from Iris to X-ray. Tobac works in both 2D and 3D, meaning X and Y and X, Y, and Z. It obviously works across time for both of those. It can identify 2D areas or regions or 3D volumes of any variable, whether it's tracked on it or not. And our website's tobac.io. I'm proud of capturing that domain. So why would you use tobac? And I'll show some examples later on. Tobac is input and grid agnostic, as I mentioned before. It is not just for clouds. I have seen, this is just a snapshot of what I've seen, people using tobac to track clouds on updrafts and model data. That was the original use case in a bunch of different computer models. Storms on radar reflectivity. The US has a beautiful network of weather radars. We can track all of those storms simultaneously with tobac. Clouds on brightness temperature from infrared, from satellites. Things like light lightning. We've been using tobac a lot more recently. Our community has to be able to detect and track storms with lightning. Very, very powerful to be able to do that in some cases. We've also seen some a little bit further out things like tracking haboobs on dust concentration. So those are those dust storms that exist primarily in the Southwest or in other more desert kind of regions. And then clouds on precipitation rates. There's new applications every day. I have seen plenty of conferences now where people are using tobac on something new and exciting that I had not seen before. And it's always cool to contribute to a package that other people are using that you don't know. And we're a relatively small package, so that's still very cool for me. So how does tobac work? One of the key innovations of tobac, beyond the fact that we work with any grid or any variable, is the idea of using multiple feature detection. So a lot of our background here derives from image processing, if you're familiar with any of those techniques, and therefore we use a lot of tools from scikit-image to do our processing. Basically, the way that tobac works is you set a physical threshold, meaning the definition depends on what your variable is. But you set a physical threshold, you set multiple physical thresholds, and tobac will identify contiguous areas that are greater than your threshold. Good. You're seeing my mouse. Okay. Tobac will identify areas greater than your threshold, even if they're relatively smaller areas. And then if you have areas within those thresholded areas that are even at an even higher threshold, it will split it apart. Why do we want to do this? Well, this is actually really powerful in cloud tracking because it enables us to detect both strong and weak storms. I'll show some examples if you've not looked at kind of clouds and data before. But when we end up with a big field of clouds, you can end up with everything kind of mushing together. So being able to detect on multiple thresholds and understand that where they all come from, but also being able to split those up into individual segmented storms is really, really helpful. And actually, here's a great example here. This is gridded radar data, gridded with PyArt, wonderful radar toolkit, from a day a few years ago in Cheyenne, Wyoming. This is Cheyenne's up here. This is the Colorado Front Range down here. This is a pretty standard day and pretty standard looking storm convection over the Front Range of Colorado. You've got, this is radar reflectivity. You think about this, the precipitation intensity, if you're not familiar. The various colors here, the more intense colors, the more greens and yellows are stronger values. So this whole thing here, by some thresholds, could all be considered one storm system. So we can take these sort of feature areas and then we can say, okay, let's look at our first feature threshold, 20 dBz. 20 dBz is a pretty weak storm, but it's still something we want to be able to track. That's the beauty of the multiple thresholds, is we can set these weaker thresholds and allow us to still identify storms in their genesis and their decay, and also capture mature phase storms and kind of split them up. If we just used one threshold here, this entire monster here would all be considered one storm. And then we actually can go up to multiple thresholds, 30 dBz, 40 dBz, and then this whole thing works in 2D or 3D, as I mentioned before. It also works across periodic boundaries or wraparound boundaries. We added that capacity in to handle that. And it also works this is all perfectly parallel, the feature detection is. We can also calculate areas of features. So using those detected features from before, we can identify individual areas around our kind of seed points. Using what we call the segmentation approach. This is using scikit-image watershedding. Again, we have a support here for wraparound boundaries, and also it is, again, perfectly parallel, and we have some tools to help support that. One of the really nice things about segmentation is that tobac now has tools to regrid your input data. So it doesn't regrid the whole input, it actually regrids some of the tobac internal data structure, which is actually a lot cheaper to do. And we can take one variable data set. For example, I've got radar data here on the left, where you're looking at kind of those storms, the precipitation intensity we saw before. And on the right here, this is the same image, same set of storms looking down from space in geostationary IR. And we can do this on the same variable, different variables, different grids even, and pull together those statistics. So tobac really excels at data fusion problems across different atmospheric data sets or different gridded data sets. Finally, the tracking is kind of what brings it all together. We use predictive tracking from TrackPy, which predicts based on feature history or motion around the feature. And this is kind of, tobac is one of those where really we stand on the shoulders of giants, and it's really wonderful that we are able to bring all these different tools together, bring them into a common data format, data output, and kind of stitch them all together to build a really really comprehensive total package using kind of standing on the shoulders of giants. This again works with 2D and 3D data and works along periodic boundaries. And we also have tools built into tobac now that will allow you to identify mergers and splits of clouds. Our final output, we have two kinds of outputs. We have tabular output from our feature position and tracking outputs. We output those as data frames. We have pandas output right now, kind of by default. I think we're working on Polar's support, and we'd like to kind of extend it to like Dask data frames. That's been a lower priority. And then we also have X-array data array as output for anything gridded. We also have tools built in that convert the data frame output to data or X-array data arrays if the user is interested. We got a lot of feedback from our users. Our users are primarily in the atmospheric and earth science community, and they really like NetCDF for good reason. It's been a standardized, very well-used format in the field. A lot of data sharing requirements are built around NetCDF, and so one of the key feedbacks we got early on was you need to be able to support this in NetCDF output, and we said, okay. It's not something I love because working with tabular data, what is effectively tabular data in NetCDF is kind of a pain, but we make it work. We wanted to support our users as much as we can. So I'm going to show a couple highlights of different projects using tobac, and then I will talk about kind of the development process and how we got here. So first off, people kind of using, this is from one of my undergraduates actually, a really nice project looking at the HER weather model. So the HER, the high resolution rapid refresh, is a NOAA model that is run continuously, run once an hour, every day, and runs out for 18 to 72 hours. Basically, the idea is we want to get what the weather is going to be like. It's run at high resolution. Basically, it's a storm prediction, very fine scale, early or getting close to the time of storms firing model. You look at it to be able to forecast weather, the storm's positions a day or two in advance. Very, very important tool for weather services, especially when we start talking about days with severe weather. The HER is one of those models where it's very difficult to evaluate performance. This is actually true on anything in the storm scale. Evaluating things at kind of larger scales easier. We can do things like z-scores on 850 millibar temperatures or something like that. But evaluating it on the storm scale with metrics that are useful for forecasters is a lot harder. So what we did and what my student did is to track both the HER model output and MRMS, which is a national gridded radar output data set. We can get the two of them to be on the same grid, and we can track both of them with tobac because tobac runs so quickly. And we actually are running it in near real time now, where we can use it to evaluate the performance of the HER model in near real time and provide that data to forecasters, and also be able to use it to evaluate the past performance of HER to understand how does the number of storms that it produces compare to the number of storms that existed in real life, storm areas compared to real life, storm motion compared to real life, and we can do this even down to region and sub-region levels, and working on writing that up now. Tobac's also being used in at least 2 planned NASA satellite missions. So first, the only one I'll talk about here is the NASA INCUS mission. So the NASA INCUS mission, investigation of convective updrafts, is a mission targeted at observing vertical motions in clouds from space. It's a set of 3 satellites planned for launch in September of 2026. And one of the products in INCUS is this product called AUX-GeoIR, which is designed in part to be able to identify these satellites run over the Earth. They have a very narrow beam width. They get a storm at a time. And the AUX-GeoIR, the tobac tracking product, will enable us to understand and put in context when those observations were taken. So we can say we get this sort of vertical motion from this storm. What part of the storm's life cycle were we in? Where did that storm come from? What was the environment that storm formed in, et cetera, et cetera? And tobac is being used to provide all of that. So I want to now kind of shift gears a little bit and talk about how we got here. Tobac was originally designed, as I mentioned, to meet the goals of a 2017 charge, track clouds in different weather models and compare them. It had significant contributions to 2 people's PhD dissertations. Well, what happened is that those 2 original developers moved on. Max works for the German train company now, and Peter has a research scientist at Colorado State University now working on problems that are using tobac, but he's not so much working on developing. And if you look at our GitHub commit history, you can see that. We have a rush of development kind of 2018, 2019, and then it stops. And actually it stops around the time that a lot of other GitHub projects were picking up with people trapped inside from the pandemic. Effectively no commits at all between 2020 until you get to 2021. And you kind of saw the tick up over time and where we kind of got back to where we were. And the story here is fairly simple. We still needed tobac. Several of us, including me and Julia and Will, were using tobac for our own projects. We weren't talking to each other. We didn't know each other existed, really. I met Julia on GitHub. We both shared code in the tobac issues because we had the same issues, and so we just traded code back and forth on the issues page because neither of us had merge rights to be able to do a pull request, and the original developers were effectively uncontactable. There was documentation online. It was not very good. But much of the need to know, there was a handful of people in all of our groups that were using this. Actually, Julia figured it out by herself. Will and I both had help. And most of the kind of knowledge there was kind of an oral tradition. We passed it down from senior PhD student to junior PhD student, and we all figured it out together. That's what kind of kept the project alive, was that kind of discussions among groups and then also sharing of code on GitHub issues. It was kind of a pseudo pull request system when we were fixing our own versions of the code. And kind of finally in early 2021, this came to a head. We tried to get everybody working on tobac into the same room, a Zoom room, early 2021. And start building towards formalized governments. And I have a rhetorical question here, which is, what does it mean to be in charge of a project? There were no maintainers. The maintainers that were around didn't pass it on to anybody, and I think they thought that no one was going to use it, which is fair enough. They got their PhDs out of it. They did a lot of fundamental, really important, great work, but we didn't have a formalized structure or plan. So we gave a few of us merge rights, and really the biggest innovation here was getting us to start talking to each other. We instituted monthly to open developer meetings, which continue to today. And by 2023, we kind of established 3 separate groups. Lead developers, which have merge rights, steering committee, which is kind of people to give overall strategy thoughts and approve roadmaps. Community developers, which is everybody that's doing pull requests and things like that. And we try to be as open as possible in the spirit of all of that. Some of our contributions are unique, and that many of our problems do not have an accurate answer or correct answer. They're kind of subjective and up to the science question. One of the most common questions I get is, what settings should I use for X? I don't know. What is your science question? You'll have to decide that for yourself. And so because of that and because of our unique history, we do almost no direct commits to the repository. Almost all of our development's done through pull requests. There's good and there's bad here. We start now reviewing contributions more closely to scientific peer review, and we do almost all of our changes through pull requests as from forks and then PRs to main for release. There's advantages and disadvantages here, and I'm happy to talk more about those more offline. I want to talk a little bit about lessons learned here. My first lesson learned is upload that project to GitHub. If tobac did not get published on GitHub, we would not be using it. We would probably have 4 new tracking tools from everybody that needed their own. We wouldn't have a standardized one that all of us were using together. Documentation, though, is key. If you don't have documentation, people aren't going to know what to do. I don't go and read code if there's not documentation unless I really need the package. Formalized governance wasn't needed for us until it was. We started instituting more governance as it felt right, and we didn't spend a lot of time on this, frankly, until we were sure we were going to be able to keep up with this, or want to keep up with it, frankly. Convincing users to become contributors is extremely difficult. I'm not good enough at coding for that is a common thing I keep hearing. I'm going to keep hearing that, I think, until I die. I keep telling people, no, you're good enough, I promise. Just you got to get started somewhere. And sustaining scientific progress or packages with graduate students is really challenging, but possible. You just have to have an influx of new users. Really here, we're moving towards a global universal track database of clouds. That is the vision here. That is the long-term vision for tobac and tracking more broadly. We have some big needs here. Multivariate tracking. Clouds are not just one thing. They are many things simultaneously. And doing things on unstructured grids, things that are not regular rectangular grids. If you have ideas or you want to contribute, come find me. I'm here until Sunday. And I'll leave this up, and if there's time, take questions.
Alrighty, encourage folks to go ahead and go on to the Slack under the track Earth, Ocean, Geo, Climate, and Atmospheric Science, and reply to that thread to ask your questions. I'll start with one since we don't have any yet. Where did you go to find information about setting up a governance structure? Like, were there any like best practice documents, or did you kind of come up with a lot of that yourself, or?
The short answer is I did not. I did like very basic Googling, found a lot of very formalized bylaws that sounded like a lot of work. And then we kind of just, it really came out naturally, to be honest. There were 5 of us that were working on code, and there were 3 of us invested for one, in one way or the other, who were heavily involved in meetings, but not working on code. And so it kind of evolved naturally from that. And that's, kind of unique in an academic thing, right? Like we have PIs that were interested in seeing the science move forward, but not going to touch the code ever. And then those of us that were really invested in getting the code move forward because we needed it for our dissertations. So we'll see how it continues to evolve. I'm sure it will continue to evolve. I don't have nearly as much time to do code anymore now that I'm a professor.
So we have one from Jacob. Lots of object tracking packages exist.
Yes.
How can we communicate and collaborate across these projects?
That is a great question. There have been various atmospheric cloud tracking meetings. Those have existed for a couple years now. I think there is a need to have all of us talking together, and my shortest answer to that is please come find me afterwards, and we can at least start a mailing list or something simple so we can all start talking to each other so that we're not duplicating work.
Great. Again, reminder, I see a couple folks typing. Any other questions? You mentioned, so this is from Nick, you mentioned building a global database of cloud tracks. Does something like that exist in any form? What's the current standard? Yeah,
that's a great question. The short answer is yes, with a big, very, very, very large asterisk. The answer is yes for some variables, for some definition of cloud. There are a handful of, there's at least 2 projects that I know of that have produced something. The problem is that when you start talking about a global database of clouds and you're doing it from relatively coarse data, you kind of alias a lot of clouds together. And I think there's also an issue of data formats there. A lot of the way that those have been historically distributed is big grid files with no statistics generated about them for many years. And so it's a little bit of a data processing problem. But yes, things like that exist, but not at as high of a resolution that I would be comfortable saying, yes, definitely individual clouds are being captured versus just big cloud system is being captured.
So Paige asks, what about tobac makes it specific to tracking atmospheric features? Could this tool be used to track other features, for example, in oceans?
Yes, the tool could be used to track features in oceans. No, there is nothing specific about it being atmosphere. Atmosphere is just the community that all of us work in. So if you are in something other than atmosphere, yes, we are very interested in hearing what your needs are and supporting your needs. Actually, I will tell a very short story, which is that when I started at UAH, I gave a seminar to the undergraduates, and an undergraduate approached me from electrical engineering and he said to me, I'm using tobac to track electrons in my PCB. And I said, you're doing what now? I don't know if that story is true or not, just to be clear, but I like to tell that story because it is true. We could be used for anything. If it's gridded data, we could be able to track it. I don't see any reason why not, but it's just come talk to us. I don't know what your needs are. We're all atmospheric scientists. I'd love to expand the reach of tobac to more broad communities.
And then Nick asks, what about DL/AI methods for tracking and classification? Is there progress in that direction or plans to integrate?
Yeah, we've talked about that quite a bit. The answer is I have seen progress in things like segment anything, and there's a couple others. The problem is getting to, like I said earlier, there's not a right answer. So getting to a training data set of this is a cloud versus this is not a cloud is a really hard problem. And I'm not saying it's not a solvable problem. I am not a deep learning expert. And if you are, please come talk to me. I want to hear more. And I think that we will move more towards that. And one of the things I kind of glossed over here for the sake of time is that, the way I describe tobac is the way that tobac works in the current implementations, we have designed all of this to be very modular. So if you want to implement your own feature detection, if you want to implement your own tracking, if you want to implement your own segmentation, or if you want to implement all of those together or separately or whatever, as long as you follow the data structure, everything is still interoperable. And I've had a few people implement their own, especially feature detection, because they know exactly what they're looking for in their feature. And so they just ignore our feature detection, build their own, but then still use our other tools built around tobac.
Great. And then last question. Can you talk more about the segmentation approach within tobac that it uses for cloud identification?
Yeah, so the feature detection code results in feature positions, which are a point type position. Those point type positions are used as seeds. We also have the ability to do seeds in a box, basically, so you know your initial position, and you can then add basically padded seeds around it. It's user settable how much that is, and then it uses a watershedding segmentation type approach, which basically works like a watershed. It starts from the point and expands outward until it either hits the end of the threshold or it hits another segmentation.
Great. Thanks so much.